This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
Hello everyone, this is Felienne for Software Engineering Radio. Today with me on the show is Jordan Adler. He has been a professional software developer since 2003. He is currently Engineering Director for Developer Engineering at OneSignal. Previously, he was API Platform Engineer at Pinterest and Developer Advocate at Google. Welcome to the show, Jordan. Today's topic is code generation. So let's start with a definition. What for you is code generation?
That's a great question. So code generation is it's a technique that you can use in software engineering where essentially your software is producing code as an output rather than some other kind of expected user behavior. So for example, a common code generation technique would be transpilation, wherein unlike a compiler, which compiles programming code into machine code, a transpiler compiles or translates programming code from one language to another. And so a common one of these would be Typescript, right? So Typescript converts, into JavaScript and conducts some kind of type checks along the way. That would be an example of transpilation, which is a type of code generation technique.
Yeah, that's immediately an interesting question. An interesting example, because that leads to the question, why are we generating source code? Why are we not just typing source code, right? So what is the benefit of generating JavaScript from TypeScript, or in other contexts, generating certain pieces of software if we can also type there, right? I get it for assembler. No one wants to type bitcode or assembler, but why JavaScript? It's fine. Why are we generating this?
Yeah, there are lots of different reasons to do that. Typically the answer is productivity of one reason or another, right? So if you are trying to write a piece of software and there's a lot of duplicate code in that piece of software, perhaps it's duplicated because you are one of 5 different teams, each trying to build a system, and they all interact with each other, and maybe they use different languages, but they all have the same kind of interface or the same specified method of kind of interacting with each other, then you might want to procedurally generate kind of that interface code so that when you actually change the way that the servers communicate with each other, you only have to change them in one place instead of 5 places. So that's a common reason. Another common reason could be to, like I mentioned with the TypeScript to JavaScript, perhaps you're conducting some kind of checks and in the process producing code that is consumable by some other tool. Another example might be, lots of folks have, Kubernetes YAML, right, that becomes unwieldy and repetitive after a while. And so there are tools out there that can actually produce Kubernetes YAML for you based off of templating. And so that process effectively generates code, declarative code that is the kind of Kubernetes consumes. And so there's lots of different kinds of reasons that people might want to do this, but typically they boil down to productivity. You have some kind of machine or some kind of system that expects either kind of a computer system or a system of people that expects kind of code to come in one way, and transpilation can kind of enable you to fit that standard, or it's a technique you can use to enable you to fit that requirement while reducing the cost of actually.
Yes, generally it's quicker, and it might also be less error prone because you can do some checking before you actually generate the code. So you're generating correct code for a definition of correct.
Absolutely. You can test for correctness. You can duplicate code, so you can kind of produce multiple different versions of the same input, right? So the process of doing that as opposed to having someone write it out, right, it's a lot quicker and less error prone. Absolutely.
Yeah, that makes sense. So you already sort of hinted at some concrete examples, but can you give us an example of a situation in which you used a code generating tool to solve a specific problem?
Yeah, so one example would be, we have this tool called a CLI tool that we've built, a little prototype. And what it does is at OneSignal, it injects kind of the code into an application to add an SDK into kind of a mobile application. So you have a code base, it's an Android app or an iOS app, for example. You can run this tool, it'll scan the software, or the programming code for that application and conduct the right changes to actually inject the required changes to the code to be able to include the SDK. So this is a kind of code transforming process technique, a code transformation, where you take one piece of code, you output another piece of code, but you've modified the code in some way. Not unlike transpilation, but the difference here is we're not converting from one language to another. We're just kind of keeping it in the same language. Maybe we're semantically changing the behavior of the application.
Yeah, so we're like enriching an existing code base with some features. And later in the episode, we want to dive into code transformation specifically as like a separate process from code generation. I'm also wondering, like, are there anti-patterns? Are there situations in which you would say that code generation might not be the right solution?
Yeah, I mean, oftentimes it adds quite a bit of complexity, particularly in your build toolchain. So if you have a situation where you think you might be able to save developer time by code generating some piece of the code base before kind of building and producing it, now that kind of adds on to your build process. So that can add time to each build that you do, both in terms of like when the software is actually shipped, but also in terms of development, right? So you have to kind of have a local development loop. You have to build, you have to test, you have to iterate. If you have kind of code generation in the mix during that kind of tight developer loop, it'll end up taking longer. And so, oftentimes the trade-off here is, yes, I'm spending a lot less time writing code, but I'm spending, a lot more time waiting for code to be generated. That is a trade-off that you have to make intentionally, and the productivity gains will have to outweigh the cost of both establishing the code generation pattern, which is complicated, certainly, and rife with issues, but also in terms of the cost of kind of using it and maintaining it, which includes quite a bit of complexity in the build toolchain and time cost in the execution of that build toolchain.
Yeah, that makes sense. And I want to talk about the whole build process of code generation also deeper in the episodes. But one question maybe that sounds a little bit abstract still for people that have never used code generation tools is like, what does a code generation tool look like? Do I write code to generate code, or is this a visual tool where I sort of click the interfaces together and then it generates code from a visual model from something like UML? What does code generation look like practically?
That's a great question. I think in practice, all of those are kind of common UIs for dealing with code generation. There are tools that you can use kind of in a one-off basis, visual tools, for example, to build out, let's say, SQL specification, like a set of SQL statements to create tables. There are lots of tools out there, table designing tools that produce as an output some kind of, SQL statement that can be consumed by, or series of SQL statements that can be consumed by a database. That is a case, certainly. Another common one, perhaps the most common one, again, going back to the IDL's case, if you have something like Swagger, which is an API specification, now called Open API specification, previously called Swagger. You can have in YAML or JSON a definition of a REST API and run a CLI tool that procedurally generates from that specification client libraries or perhaps servers, or pieces of server code that is then consumed by a Java application that fills out the stubs of those, of that interface, right? So it can vary in terms of interface. It can be CLI based, it can be GUI based, it can be something you use once as part of your development process and never use again. It could be something that you use every single time you build, and it could be something you use manually when you need to pull something in from upstream. It's a technique that can be used in many different ways for sure.
Nice. So that gives us a lot of ways to apply code generation in projects. Now we have generated code. So the code has been generated with one of the variety of the tools that you just described. So now what? Do I manually read this code? Is there some sort of verification, or do I verify the generation? What do you do in that case? Like, do you ever look at the generated code? Is it ever necessary to inspect that, or is it sort of correct by construction?
Oh, absolutely. And, you can establish a pattern by which you can kind of procedurally generate code and then have that be tested in a way that, enables you to build confidence that it's error-free. For example, when I was at Pinterest, we were using code transformation to convert our code base from Python 2 to Python 3. That was part of the migration that we were doing at that time. And that process, as we were kind of converting bits and pieces of the code from Python 2 to Python 3, well, we could, deploy a piece, to convert a small chunk of it, deploy it to a portion of our overall fleet, let's say 2%. And then if 2% of our fleet is running this new version with these new modifications and it's getting all the same, API requests and returning all the same outputs and not having any new errors, not producing any new issues, then we can probably say that it's safely kind of consistent between the two versions and we can deploy it. So in cases where you have kind of a deploy process where you maybe canary-like or have some other processes statistically eliminating kind of risk, and you can move forward carefully, then automating the process of deploying code generations is not unreasonable.
Yeah, so I wanted to say, like, this is a situation in which you already have running code. You have a baseline, right? You know what it's supposed to do, and you can migrate parts of it. But this is, of course, not always the case. So I was wondering if you also have examples of experience with sort of freshly generating code where you do not have a baseline to test against.
Oh, absolutely. And in most cases, you really should manually inspect the code. So even when we were working at Pinterest on this tool, this project to convert from Python 2 to Python 3, we were routinely manually inspecting the changes that were coming through. And honestly, like some of the code transformation we had, they were not error prone at all, right? They were fairly straightforward. Convert this function, add parentheses after print. Right? So print is no longer a statement. Now it's a function. That's a pretty straightforward thing to change until you start throwing in complexities like, well, what if we have our own function called print that we shadowed, right? So we have kind of, monkey patched our own print function. Or what if we have some kind of special label in our code called print, that we've modified some way so it's not keyword. Or what if we have function calls that look like print and perhaps the regex that we use to convert the code or whatever technique that we use to actually implement the code transformation was a little overzealous. And so we have error. And so we'd often kind of run through and manually review all the changes as part of our PR process that would actually happen. However, if you were to run code generation in automated fashion, for example, we have at OneSignal API client libraries that I mentioned again that we procedurally generate from OpenAPI specification files. And so the output of that can change from version to version as we pull in, changes from our upstream OpenAPI generator, open source repository. We pull them in manually, we rerun the code generation, and then we review the changes that occur kind of before landing them because you can't say for certain what the changes will be. So that is more of a manual kind of review process than something like the kind of the canary-based or even kind of the PR inspection, which is much more kind of scrolling through thousands and thousands of changes and looking for outliers as opposed to kind of really deeply inspecting every single line that's changed, trying to understand it and understand the impact.
Yeah, that makes sense. And I guess there's also a difference between if you are the person that is authoring the code generation tooling, or if you're simply using something that has been extensively tested, and probably you can rely a little bit more on the fact that the generation will be correct because it has already been tested by many other people.
That's a really great point. And I think you've hit on something interesting about code generation, which is that it often involves, collaboration between people. It's a technique that is pulled out when two teams or two groups or two pieces of software have to interact with each other, or two or more, really. And so having that kind of consideration of, okay, where is this code coming from? Who wrote the code generator? And understanding that is as much of a process of understanding how to integrate and deploy this technique in your code base as anything else.
So let's talk about practicalities. Yeah, you already mentioned that this code generation will then be part of your build process, which might be time consuming, but also you get some interesting questions like, what do I do with the generated source code? Do I check this in to version control? Or is this typically something that you would put in a git ignore because, well, if you need it, you can just generate it again? I can imagine that for reasons of traceability, maybe you also want to ship the generated code so you are sure that everyone looks at the same version of it. What are your best practices there?
Yeah, I think it is going to vary. I don't think there are kind of standard approaches. Again, it's an unfortunate answer. I think, when it comes to code generation, code transformation, and really kind of more broadly, compilation and kind of the consideration of kind of managing code, there are lots of different ways to kind of treat code as data and lots of different patterns of kind of using that. I have seen cases where people have kind of generated code, and then, for example, in Java, right? And then created, modified the exact same file to change out the stub, functions to actually implement them. And then on kind of updates to the API, where you can kind of then procedurally generate the changes to the server function, then you can just kind of get a patch file, run that against your file, and then manually edit it, right? So that can work. You can have kind of good mixed code in the same files if you're going to be manually editing and manually reviewing it. If you're going to be automating it, I probably would not kind of have them be in the same files. I probably would also, whether or not you checked it in depends on whether, the generated code is more of an intermediary object or more of a kind of desired output of some kind. And so that will depend, right? So, example, in the API client libraries, the generated code, is the product, right? And so for us, having that be checked into the version control actually makes sense, not in the repository that contains all the code that generates it. So we have a code that one repo where all the code is generated for the client libraries, and then let's say 10 other repos for each of the client libraries, right? One for each of the other client libraries: Java, Go, C#, Rust, and so on. And so the reality is that you will need to kind of use whatever approach makes sense. My only cautionary statement here, and kind of the good rule of thumb here is, when you're working with a language that's typed, you want to take advantage of that typing. And if you're using code generation in a way that basically creates an intermediary layer between the procedurally generated types and the types that you're actually using in your handwritten code. In other words, if your handwritten code and your generated code have kind of two totally different type graphs, and they are not connected at all, then your type checker is not really doing its job. And that's a problem. So you do have to be conscious of that. But other than that, I would say there's no kind of hard and fast rule, and it really depends on the situation.
Yeah, I think I can add an example there from a project that I work on myself, because sometimes it's also about like, what tooling do you expect people to have? So we have a backend that's in Python, and most of our open source developers actually work on the Python side. And then we have a little front end that's written in TypeScript that we then transpile to JavaScript. So we do check in the generated JavaScript because we think that it's a hassle for the Python developers to have to generate the JavaScript themselves. It might not have NPM. It might just not be ready for that type of tooling. So it's like a courtesy to people who are like, oh, here's the generated code. If you're not changing anything in the front end, you don't need to compile or transpile the code. So sometimes it's also about, do you require the users or the contributors in your project to also install all the code generation tooling, which might sometimes be also complex to deal with. So that's maybe also a consideration that you can have, that not only who will or who needs to generate the code, but also who will sort of feel like installing all the tools that make the code generation happen.
That's a really interesting point. And it kind of actually, interestingly enough, is an illustrative of the difference between kind of commercial applications of this technique and kind of open source or academia, where you want volunteers, you want people to join. And so you want to kind of minimize the cost, the threshold effort to contribute code. And that's not true necessarily in a commercial setting where I've been doing most of my practitioner work, right? In a corporate environment where I can say, well, tough.
Yes. You just have to do what I say. Yes,
right.
Exactly.
Install this thing, or I added it to the device management. So you don't even realize it, but you already have Java compilers or JavaScript compilers on it.
Yeah, because sometimes this can really be a big blocker. Like I was looking into another code generation tool, and then it's like, yeah, you have to install Eclipse and this version of Java. I have never used Java. And then it's sort of a need for open source work. It is a threshold. It's like, well, if it requires me to install Java, then I don't feel like doing this. Maybe it's not worth it. So that tooling angle, and it's very right that you point this out, is very different in open source projects, where indeed we want to make it as easy for you as possible. We don't want to force Python developers to install tooling that are like, what is this and why do I need that?
Yeah, that's a great point. There are lots of kind of toolkits out there for, open source toolkits for generating or building code generation tooling. One of them is called Yellow Code, which is written in JavaScript or TypeScript rather. And that one is one that we ended up using for a lot of our web SDKs. So we kind of procedurally generate glue code that sits on top of our web SDKs specific to React or Vue or Angular. And so, we're able to produce those kind of procedurally generate higher level SDKs for these frameworks on top of our web SDK. But we didn't want to do that using the same kind of Java-based tooling that we use for our backend stuff, right? And so Yellowcode is this really nice kind of TypeScript tool chain that exists for building these things. I have to imagine to some extent it exists in part because of what you were saying, right? Like, a lot of these things existed beforehand, but none of them kind of in the same tool, with the same consistent, exactly, or compiler tool chain or so on.
Yeah, we will definitely add a link in the show notes to that Jellycode tool. Then I was also wondering, what about documentation, right? So if I'm generating code, where does my documentation live? Do I generate documentation that's in the generated code for when people inspect the generated code? Or is that documentation typically placed wherever I'm writing the specifications for the generation, whether that is in a different programming language or in a visual tool? Or is this something that lives in a markdown file where it just says this is how you generate the code and this is what happens? Are there any best practices there?
Yeah, I mean, I think that the best practices when it comes to documentation is yes. All of them. I think it'll depend. So to give you an example, we'll often procedurally generate, like I said, API client libraries, right? And that includes our API reference in it. So we have kind of, a Python classes that are stubbed out that include doc strings or documentation kind of inline as Python developers expect them. And that comes from our YAML file, the Open API specification kind of YAML file that says, okay, this, if you call a put on this path on our server, that is actually this function, and here's what it does, and here are the parameters, and so on. And so that kind of YAML file is consumed, procedurally generates, and actually creates the client libraries. And so we have kind of one place where we kind of update those API reference documentation and can then propagate that downstream to 10 different client libraries very easily. So that's one place where documentation exists. And so that's kind of that inline, documentation in kind of the resultant client libraries. We can also procedurally generate just an API reference itself, right? So kind of a markdown, think of it as instead of producing a TypeScript output of this kind of API specification, we're producing a markdown output. And Open API Generator, the open source project, includes kind of an output so you can procedurally generate markdown documentation or other kinds of documentation, actually, to be able to host and serve kind of alongside the client library. So that's kind of another form of documentation. Yet again, we also have the documentation in the Open API Generator project itself, which explains how to use it, right? So that's kind of one piece. But in our own kind of repo where we host all the code that actually executes as part of our toolchain, Open API Generator, and includes all of our patches to the downstream libraries, that repository also includes instructions for people who are working on our client libraries on how to specifically use it for us, right? Which includes, by the way, how to patch the README for the resulting client libraries to have kind of manually crafted READMEs, because the procedurally generated client libraries from the upstream templates are not always kind of super useful immediately. So there's documentation, API reference that's being kind of inserted into the code that's being resulted, as well as produced as an additional target that we can serve alongside our client libraries, as well as the documentation that exists for the developers using are working on our system and not the ones that are consuming the code produced by the system.
Yes. Yeah, so indeed there are these different forms of documentation. That's probably a good idea to have it anywhere. And if you have specification about what you're going to generate, you might as well generate that specification as a comment in the general code. So let's go from code generation more towards code transformation. We have already talked about this a little bit, but what exactly is code transformation? Now we have a process in which the input is code and the output is also code, but then there's also code defining the transformation. So what does code transformation look like for you?
So if you think about kind of code generation, code transformation as both things that output code, right? Compilation also outputs code, right? So compilation takes in programming code, outputs machine code. Transpilation takes in programming code, outputs programming code, maybe in a different language. Code generation takes in something semantically and outputs code, right? It doesn't have to be code. It can be some kind of configuration object or something like that. Code transformation, however, takes in code and outputs more or less the exact same code, but having been modified in some way. And so code transformers, sometimes called code modifiers, you'll hear them called code modifiers, they can take a variety of different shapes in terms of how they're implemented, but really what they try to do is produce something that's basically the same language, but with some modification in the code itself, either semantically in the case of, say, a code transformer that's trying to change the behavior of a function, and maybe you have to change everywhere it's called as a result, right? If you have a very large code base, you might not want to do that manually. You might write a little code transformer to update, the function and everywhere it's called to change the parameters that are being passed around. So that is a kind of one consideration of code transformer, about how code transformation is different than kind of other techniques in the space.
Yeah, so your example made me think of a refactoring, right? So adding a parameter or changing the order of parameters. This is something I can do in the IDE. I right-click a function in most IDEs, and then I can reorder the parameters. So that is a refactoring, but also a code transformation. Like is a refactoring an example of a code transformation, or is it not because it's not really done with a code generation tool?
I think refactoring is a common goal or common cause or use of code transformation. You talk about find and replace in the IDE. So if you pull up Eclipse or something, you go find and replace. That is a code transformation, right? You found code, you've replaced it. A switch statement in Vim, that's a code transformer, right?
Nice. So then we've identified one tool to do code transformation with, the IDE. But I guess there's also other tools in which we write code to script the transformation or to visually manipulate the transformation. What are tools that you typically use for code transformation?
That's right. So if you take code and you're trying to transform it, the tools that you will use will depend on the language itself. So I talked a bit about yellow code before. Yellow code is kind of a toolkit for parsing. So it's a toolkit for making code transformers. And so it has elements of it that enable you to parse languages and represent programming code in a given language, say Typescript, as a data object of some kind. And really, if you think about, okay, what is a code generator? What is a code transformer of some kind? Well, it's really a two-step process, right? Step one, get code into data. Step two, get, three steps if you're transforming it, right? Munge that data somehow. And step three would be kind of producing or outputting that data back as code again. And there's lots of different ways that you can do that and lots of different tools that you can do that with. You can roll your own, certainly, or you can use compiler tool chains that often have that first step covered and that third step, which is convert code to data and data back into code.
And then what you are manipulating in between is the data representation, which will often be a parse tree, I guess.
So it can be a parse tree. So now we're getting kind of deeper into kind of parsing, and for folks who have taken compiler classes, you might remember some of these things, but you can use an abstract syntax tree, which kind of includes enough of the information for you to be able to take, a representation of programming code and turn it back into source code. Because remember, not all representations of programming code can be turned back into source code. Once you've stripped out white space and comments and so on, you can't, immediately turn it back. And so a lot of compilers will have kind of actual multiple steps. They'll go abstract syntax tree, then they'll trim that down to a concrete syntax tree, then they'll transform that into bytecode of some kind that actually gets piped into, say, the JVM or Python's virtual machine. But in our case, we're going to go part of the way. So for Python, as an example, we can actually use Python's AST module, the thing that Python itself uses to represent Python programs as code. And pipe code, read code from text, put it into there. And then once it's in that AST kind of class, then we can modify it as we like. But there are other ways too. For example, you don't have to use kind of a complex compiler toolchain. You can just use regex or even kind of look for strings and kind of manipulate strings. Really, any way that you can kind of manage string or text as strings, you can use for code too. But the less context aware that your implementation is, the more risky it is in terms of the error proneness of the output. and the less kind of, because you have to imagine if you're going to be running this code transformer on multiple different kinds of code bases, not all code bases are created equal. If you test on a million lines of code, but a particular pattern was never seen, there's some bug in your kind of transformer that you just don't know about. And it won't be encountered until someone else picks it up and uses it, and they may not be well equipped. And so you have to think about that as you're designing your transformer. But certainly the simplest possible implementation could be, a bash script that is basically a one-liner call to, a find and replace and set or vim or something like that.
Yeah, and of course it can be easy, but also more error prone. If you are transforming Python 2 to Python 3, then you just want to add brackets around every print. You could do that with a little bit of string magic, but then maybe you're not really sure that every print you encounter is actually really the print that you want to transform. So let's talk a little bit more about this case study, because you have worked on this Python 2 to Python 3 transformation project. And I would love to hear more about like did you do everything automatically, or were there some edge cases that had to be transformed manually? And what was your approach? Can you just take us through that project, how you approached it?
Absolutely. And so I talked a bit about this project at PyCon a few years ago. I want to say around 2017. You should be able to find it online if you'd like.
Oh, cool. We'll add a link to the show notes.
Excellent. Pinterest Python 2 to Python 3 migration. And we used a tool called Python Future, which is produced by an outfit called Python Charmers out of Australia that I've been collaborating with. And Python Future includes a number of things kind of related, or tools that are useful for this endeavor of going from a Python 2 to Python 3 kind of system. The first is a set of code transformers, code modifiers that kind of take Python 2 code and convert it into Python 2 code, but in a way that is more aligned with, or more gradually, incrementally more, consumable by Python 3, right? So there is a set of things that are syntactically different between Python 2 and Python 3. As an example, print moved from a statement to a function, so you have to put parentheses around it now, right? So it's no longer a special case function call. So that can be done with a code transformer. And Python actually included a function called __future__, which in the Python world we'd call dunder future, dunder for double underscore, dunder future. So dunder future is a directive that you can put into your Python code to say, okay, I'm going to run this under Python 2, but I want it to behave like Python 3 for this specific kind of change. And so what we did at Pinterest was we went through these code modifiers, code transformers, and kind of left our system running on Python 2, but incrementally made it more able to run under Python 3. And it starts with these code modifiers and these kind of directives to the Python 2 compiler that says, or Python 2 machine that says, behave more like Python 3 in this way, right? So kind of incrementally including backwards breaking changes from a future version. Kind of hard to explain, but you'd have to imagine for a moment that essentially we're kind of choosing to kind of gradually cause that breaking change to occur. A lot of that was added, by the way, in Python 2.7, which kind of came out after the Python 3. So this was all added kind of after the Python 2 migration process really started. Python 2 to 3, which was years before Pinterest really engaged in. So Pinterest is one of the last companies, in part because of the size of the code base, to engage in this process. And so it starts with the code transformers. You manually, kind of incrementally make it more able to run with Python 3. Then we have the Python Future project includes some what's called future. So it's just instead of __future__, it's future. So from future, import, so on. And you can import monkey patch functions. So for example, you can import a version of the string object creating function that creates string objects that are more like Python 3 than Python 2. Once you produce Python 2 code that behaves more like Python 3 and is running under Python 2, then you can start bringing in these future functions or future classes that are basically runtime shims that model the behavior of Python 3 under Python 2. So you can start coding against the Python 3 API in your Python 2 code base by pulling in kind of new stuff into Python 2 from Python 3.
Yeah, so you can migrate while you're also adding new features to this existing code base. That's what you're saying, right?
That's right. Yeah, you can migrate while using features that would typically not be available on Python 2. Or specifically the API that changes under Python 3, you can pull in more and more of those changes, either through directives to the Python virtual machine or through these kind of effectively user space implementations of core Python objects that are consistent between Python 2 and Python 3. This is in contrast, by the way, to another approach that you can use to do the Python 2 to Python 3 migration, which is basically if statements. You can say, if Python 2 do this, if Python 3 do that, right? And that kind of pushes the complexity into, or makes the complexity in our code base as opposed to kind of this module that we're using in library instead.
Yeah, because if you have the complexity in the code transformation tool, at one point, hopefully you are done. So then you no longer need that complexity, and then you end up with a cleaner code base that is 100% Python 3.
That's right. So when at the end of this project, the final stage, when you're actually taking this code that could run under Python 2 or Python 3 by virtue of these directives to the virtual machine, as well as these kind of user space versions of Python 3 classes and functions, you can take that code, run it under Python 2, run it side by side under Python 3, confirm that they behave the same, and then, actually stop running under Python 2 and then remove all those directives that are, the cleanup patch is a lot smaller, right? It's just remove a few lines from the top of each file that remove those directives.
Yeah, so let's talk about tools for this project. So what did you use to write the transformations in, or to define the transformations with? Was that this Jellycode tool that you were talking about? Because that was a JavaScript tool. Did you use that here, or did you use something else?
Yeah, so Jellycode, it is TypeScript based, it's JavaScript based. So it is not what we used here. It also, I think, came out a little bit later. So Python Future uses the AST class that exists in the Python standard library. So this is actually the thing that Python itself uses to parse Python. We use in Python Future as well. And we take in code, we read it in, use the AST module to kind of read in code, turn it into an AST object, which is an abstract syntax tree. And then we transform it. We look for specific, so we do like a typical tree walk. We look for example, maybe look for a node that is a function call type. And once you've found a node that is a function call type, you want to find out what function it's calling, and you can pass in, say, print, right? So you can write a little piece of code that says, hey, once you've gotten the abstract syntax tree, look for the node that has a function call of print. And then once we're in there, then we can change the AST in some way. But if we never find it, then we don't do anything.
So this is tooling then that sort of depends on a certain programming language. Does this exist for any programming language? Can you transform Java with a similar programming language? Does this exist for any programming language? Can you transform Java with a similar approach? Or is this a very Python thing to have built in?
This is definitely a very Pythonic thing, right? Most compiled languages don't have some, version of this. Most, or maybe most is kind of I'm not sure if it's most, but many interpretive languages do. So Python, Perl probably have some version of, an abstract syntax tree class or some way to model Python code or Perl code or PHP code, for example, in that language itself. But most of the time you won't see that. And in fact, compilers, you may have to reach for kind of a compiler toolchain to dig into there. So for example, LLVM is a kind of compiler toolchain project that's out there and has what are called compiler front ends, which basically take in source code as text and produce what's called an intermediate representation, which is kind of code as data in some way. And you can use LLVM front ends often. In fact, for some code transformers, I'll use LLVM because LLVM has amazing coverage on the front end side. And then so basically your front end is take, let's say C# code, turn it into LLVM, intermediate representation, and then your back end is just turn it back into C# code. So you can just write your own little, fake compiler that calls the LLVM, hey, turn this C# code into intermediate representation, then modify that intermediate representation and turn it back into C# code.
So what is a scenario that you would want to do that where you use this? Is this purely about using like compiled languages, or are there other differences between such a tool and the Python tool?
In this specific case of, let's say, an LLVM IR and an AST, I don't know offhand what they might have in difference. Now, it is. I mentioned earlier, there are representations of code as data that are not easily converted back into source code because they don't have, those white space or comments or other parts that frankly aren't meaningful to the machine, right? If you're actually turning it from source code to machine code, like if your tools that you're using to build your code transformer is really intended for code compilers, then you may not be in a good situation. But you can find versions of this for almost every language that's out there. And it'll be very kind of tech stack specific, and so you'll have to do your own research. But those are some of the ones that I've used.
So, of course, we want to also know about the pitfalls, right? What are some of the things that you ran into when doing this big migration? What are some of the mistakes that we should not make?
I mean, I think probably there are lots of pitfalls. I think probably the most immediate one that comes to mind is, not all two use cases are going to be the same. So you have to remember that, right? When you're reading documentation about code transformation of some kind, you will find instructions or guidance that is generally true, but may not be true for your specific case. Keep in mind that, when I was working with Pinterest and we were transforming a multi-million line code base, we found everything, right? We really battled hard. We battled hard in the hell out of that Python future project. And, I think that you have to be conscious of that whenever you're working with code transformer code out there is whatever you're picking up, chances are, it hasn't been applied on code bases as unique or as varied as kind of, the totality of all code in existence. And therefore, how it applies to your specific code may not be how it is intended to apply. And there are probably bugs in there too. So I guess, as there are bugs with any kind of software, bugs that exist in kind of code transformation software can be very difficult to detect if you're not kind of being intentional about it, and can be extremely difficult to debug because it's basically like, code's removed, your code's changed, it's just really hard.
So talking about transforming multi-million lines of code projects, what about performance? What such a transformation, did it take like an hour, a day?
Well, in the case of Pinterest, right, our migration took months, probably on the order of years, frankly. You have to think about the project that you're embarking on, what you're trying to achieve, and kind of what your output is, what your desired outcome is before you reach towards a tool. And if you find yourself in a situation where, code transforming gets you, more confidence as it did for us in Pinterest way, or kind of, less manual work as it did for us in Pinterest, then great, right? So a multi-year project was cut down into something that was fewer years, right? But the running of those tools, those manual code transformers, was just one part of that project. And so you have to kind of think about how your project shape is going to be different if you use this technique. If you are trying to make a change and you're pulling in code transforming as part of that change in an automated way. So if you're incorporating code transformation as part of your tool chain, for example, that will, as I mentioned earlier with code generators, increase your build time, and so that can become problematic as well. So yes, they can take time to run. There is a performance cost here, and depending on how you apply the technique or kind of what you're trying to achieve, the trade-offs may not be there. And they may end up being, yes, it takes longer to actually run the command, and I'm spending more time waiting, but I'm spending less time typing the same things over and over and over again. And so that is the trade-off that you have to think about. And sometimes that takes a view of the timeline, a temporal window that is bigger than just the build step or just the actual part of running the code itself, the code transformer.
Yeah, so I guess what you're saying is that running the transformation itself in such a big project is not really where the performance issues exist, because in such a big project, it's just maybe if it takes an hour, doesn't matter if this is a project of a few months.
Right. And also like we chunked it up. So we ran, 10 files at a time, for example, out of thousands of files. And so each run on each file may have taken a little bit of time, sure, but that process of chunking it up and doing it in that way and having some automation there netted out with something that was much faster than if we had manually done it.
So you already mentioned something about making sure that the code was the same because you can deploy it to a subset of users and see if not too many errors occur. But that is like the code as the running artifact. But I was also curious about sort of the code as an artifact for reading. Did you also make any improvements while transforming to maybe some stylistic issues? Did you also try to improve the code base, improve the readability of the code base, or at least not make the code readability worse? Because the interesting difference between transforming code and generating code is maybe with code generation, you don't necessarily need to then maintain the generated code. But with these sort of transformation projects, then once you're done, people will then manually continue to work with the code that you've transformed. How to make sure that this transformed code is reasonable for a person?
Yeah, I mean, I think I talked a bit about earlier abstract syntax trees and concrete syntax trees, and how one major difference is that they include white space and comments, right? The parts of the code, source code, that are not relevant to perhaps the machine itself that's running the code, but rather to the programmer who's reading it. And so if you have a code transformer that eliminates those things, that removes them, right, then the output code that you have is going to have those things stripped out, and that's going to become less useful to the developer. So certainly that is something that you have to be conscious about when you're running a code transformer. Is you don't want to eliminate or change too much of the white space or comments, certainly if you don't have to. There also exists a set of tools out there called auto formatters or prettiers or something like that, sometimes called tidy tools. Or think of it kind of like a linter. So if a linter does static analysis, which is basically turn the source code into data and inspect it somehow and return a result. This is bad, or this is a bad call, or this is a broken pattern, or this looks good, or whatever, right? So that's a common linting case. A prettier will take a code, actually add white space as needed, or comments, where appropriate, break up lines, do whatever, change semicolons where optional, all the stuff that are stylistic changes that historically people would spend lots of time arguing in comments on pull requests over, hey, no semicolon here, but it's optional. I don't care. Now we have basically a tool that you can run before you check in code that kind of auto pretties your code. So there's prettier in JavaScript land. Black is a tool like this for Python. And I think you're going to see something like this in lots of different languages, where there's a sort of okay, the open source community has said, here's the style that we want to more or less standardize around, because every little shop having their own opinion and having a config file in every repo, for the Typescript specific to my code base, doesn't actually improve readability, right? In the sense that what really makes a difference for readability is that everyone expects code to look like a certain way, and people can quickly look at code like, okay, I see this pattern of call visually, and so the cognitive process of looking at a piece of text and recognizing calls in a certain way is a lot better when there are markers present or the spacing is as expected. And so it's really important, certainly for productivity, not to eliminate that stuff. And I think if you have a code modifier that you produce and it removes white space and comments, it is broken, right? Because a is not really, unless that's a desired goal, right? In which case you probably shouldn't be shipping that little thing anyways, because it's probably a part of a bigger thing like a compiler.
So I guess what you're saying is that you want to keep comments in place, you want to keep white space in place, and in some situations you might want to, if you're transforming anyway, also run the code through a prettifier tool so that the output looks the same in similar cases, making it easier to read for future developers.
Yeah, and if you're doing a large transformation project, you'll probably want to do that prettier run before, right? Because a prettier, an auto formatter, it's supposed to be a semantic no-op, right? It's supposed to have no change to the semantics of the code. It just looks different. And so doing that first and then running that big patch out the door, semantic no-op, you can make it change easily. Then you create some sort of toolchain, CI/CD kind of process that auto pretties code before it gets pushed up, then that will kind of minimize the thrash to developers in your code base.
Nice. That's really good advice. Just peeking at my notes. So this was actually everything I wanted to talk about. Is there anything we missed? Any important tips or best practices or war stories that you have to share about code generation or transformation?
I think that, I talked a bit about kind of the different techniques for actually kind of getting code from text into data. We talked about regex. We talked about kind of using text markers or an AST. And for folks who are interested in learning more, that is a great place to start. Start by playing with code, take some script that you've written, see if you can turn it into some sort of data object in one way or another, and try and manipulate that. And you can use tools that are out there for your benefit. But if you're really, if you're trying to learn and grow what I think it's great to build something yourself, even if the tooling is out there already. So I would definitely encourage people, get curious, check it out. It doesn't take much to try and practice this technique. And once you've kind of learned it, you'll find yourself with a new tool, a new power that you can use, really a superpower that you can leverage to make not just yourself more productive, but all the people you work with too. And that's a win-win.
I think that's a great closer of the episode. Knowing how to parse and transform code, it is like a superpower.
Oh yeah, definitely.
So any places where we can read more about you, like your blog, your Twitter, any links we should add to the show notes?
Absolutely. I have a website, jmadler.dev. And you can also find me on Twitter. Twitter handle is Jordan M. Adler. And you can learn more about the Python Future project, which you can have the links in the show notes as well. Python-Future.
Yeah, we will make sure that those are all in the show notes.
Fantastic.
Great. Okay. Thanks for being on the show today.
Thank you so much.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.